Hello and welcome to another video in the Power P series from movingelectrons.com. Our topic for today is power flow, also sometimes referred to as load flow. Now, power flow studies are extremely interesting to do and they are extremely important as well. They, along with probably short circuit studies, are one of the first set of studies you would do when you begin to analyze a power system. And it's a topic which is very wide. It has a lot of concepts, a lot of math involved as well. Today we're just going to touch on one of those many concepts, which is the different types of buses that are used to define a power system. So let's read the question first, and then we'll go into a little bit of the explanation. For the interconnected 6-bus system shown, which of these given statements is true? And we'll get to these statements in a bit. So this is a 6-bus system that you've been given. And these are the quantities on each of the buses that are known to you. So for example, on bus 1, you know the voltage magnitude and the voltage angle. On bus 2, you know P and V, so you know the real power as well as the voltage magnitude. So there are two quantities known and there are two unknowns. And that is what basically defines or differentiates one bus from the other. So there are three different types of buses. There's the slack bus, there's the generator bus, and there are the load buses. And here in the statements, we've been given different combinations, whether 2 and 4 are a slack bus or 3, 5, and 6 are a slack bus. So what we'll do is we'll try and understand what these different types of buses are, how we define them, how we differentiate between them, and that's kind of be the focus. That will be the takeaway from today's video that I'd like you to go home with. Before I get into that though, let's quickly let's just try to understand what the power flow problem is. I know it's not really directly related to the question, but I think it'll be good for us, for those of you who already know, to kind of review, and for those who don't, to get a good primer on what it is. So let's begin first by saying what is really the importance of a power flow study. So the first thing is it allows for planning of future expansion. So for example, we said this is a 6-bus system. Let's say tomorrow there is a commercial setup that's going to come up 100 kilometers away from here. We're going to have a 7th bus. A load flow study or a power flow study allows us to see whether the new load that's being connected, that can be connected safely to this existing system, whether there is sufficient generation on the system, whether we need to have two feeds going in, if there's a transformer, what kind of transformer taps we would need, and things of that kind. It'll allow us to answer on any of the future expansion that we're planning on the existing power system. Also, what it does is it helps us in determining what's the best or optimum operation for the existing power system. So for example, it allows us to see if there's a generation connected here and a generation connected here, whether we should feed the loads from this transmission line, whether we should go through these transmission lines. It also helps us to understand what would happen if I want to plan, for example, maintenance of this transformer, or if due to a certain fault this transmission line goes away, whether I'll continue to be able to use my existing generations, whether I'll be able to exist to feed the existing load. So if there's an existing system, what will happen to it? It allows us to determine that as well. So that's where a power flow study is very, very important. What are some of the equations that are associated with a power flow study? So I won't get into the derivations really, because again, I'll try to do a separate video where we get into the math of load flow, and that's has to be a little bit more detailed. But let's quickly see what the equations are. So if you Let's say you have a, let's say this is a bus, and you have some generation connected to it. So you can, on a bus you can either have a generation or you can have a load. So let's say this is a substation. Here it has a generator, and then there are some auxiliary loads for the substation, so that's the load. Now the power going into this bus is, let's say, the scheduled power, and let's call this bus I. If bus I is then connected to n number of other buses, the total power it's supplying or taking in from these n buses is, let's say, P of I. Now, what we should have is P of I minus P scheduled on bus I. So that's PGI, PDI, and P schedule I. So let me get that out, and let's say P scheduled on I, which is equal to Pi minus, now P schedule I is nothing but the generated power on that bus minus the load that's there, and that should equal to 0. That's what you would imagine here, right? Whatever power you're supplying into this bus is what's going out to the n different buses this is connected to in an n bus interconnected system. Similarly, for reactive power, you would have a scheduled reactive power, which should be equal to your reactive power that's going to the n buses, and therefore the summation of that should be equal to 0. These are what are known as your power balance equations. So these are power balance equations. How do we represent P of I and Q of I mathematically? Let's look at that now. So P of I can be written as summation of n equal 1 to, if there are n number of buses, then you would have y I of n, vi, vn magnitude, and cos of theta I of n plus lambda n minus lambda I. And similarly, Q of I would equal summation of n going from 1 to n, y I of n, vi, vn magnitude sine of theta I n plus lambda n minus lambda I. Y of n here is the admittance, so that y is equal to 1 over z. So if there's a I and j, then this has an impedance, this transmission line. Admittance of that transmission line I of j is 1 over zi of j. And again, as I mentioned, I'm not going to go into the derivation, but I'll quickly, now these equations are known as power flow equations. Where they come from is from our formula of complex power. We know complex power S is V I of I conjugate, which implies S conjugate would equal V conjugate I. Now we know I is from Ohm's law V over Z. V 1 over Z is Y, so this is YV. So we substitute this in here, and when you do an expansion of S is equal to P plus JQ, which implies S conjugate would be P minus JQ, becomes V conjugate YV, and then you do an expansion of that for n buses, and basically you'll end up with a formula like this. So that's where we get the power flow equations from. So the objective of a load flow study, or the load flow problem as such, or the power flow problem as such, is to calculate the voltage magnitudes and the voltage angles on all n buses. So in this case, for example, for all these 6 buses, such that on each of these buses the power balance equation is satisfied. Let me state that again. You want to calculate your voltages and your voltage angles on each of the n buses such that on each of those buses the power balance equation is satisfied. And how is this done? So let us see. So we see the equations here. Number 3, the how. The how is done using iterative algorithms such as these you might have heard of. So you have Gauss-Seidel, then you have your Newton-Raphson, then you have fast decoupled. These are just some of the few most common ones that are used. So most of the load flow studies, because even for a 6 bus system to do it by hand is basically not possible. And you can imagine for a power grid with a lot of buses, to solve this problem by hand is not possible. So you use software, um, and you have various software like you must have heard of PSSE, ETAP, and many others. And if you go to any of these softwares, they would ask you what kind of an iterative algorithm that you have to use amongst all of these. So these are how you solve this, and in the background of these software they're running these equations. As I mentioned, there would be 2 quantities that you would know and 2 that you wouldn't know, and that is what differentiates the buses. So let's get to the main discussion, the types of buses that are there. So that there are 3 types of buses that each system is defined by. So you have your load bus, you have voltage controlled bus, and you have what's called the slack bus. A load bus is also known as the PQ bus, and we'll get to that in a bit. A voltage controlled bus is a PV bus, and a slack bus is a V delta bus. In general, these are the quantities that are known on each of these buses, and the other 2 quantities are unknown. So there are 4 quantities that we find out. There is the voltage magnitude, the voltage angle, the real power, and the reactive power. The admittance is a physical property of the system that would be known, whether it's the source, whether it's a transmission line, whether it's a load. So the 4 unknown quantities are P, Q, V, and delta. Here theta is the angle of the admittance. So a load bus is a bus that has no generation is connected. So which implies PGI and QGI on any of this bus is 0. And therefore there is a load connected. When you have a load connected, you know your PDI and QDI. If it's an existing bus, you can take measurements and you know what your load, real power and reactive power requirements are, or it could be on the nameplate for motor, for example. If it's a future expansion, as I mentioned, if let's say you're connecting a 7th bus here, which is a commercial setup, then you would know through load forecasting and historical records what you can plan for. So your known quantities are P and Q, and your unknown quantities on a load bus are V and delta. Voltage controlled bus is any bus where the voltage is kept constant. So voltage is kept constant. So any generator bus, for example, would be a voltage controlled bus, because in a generator you can control your power, your real power from your prime mover, and you can control your voltage using the generator excitation. What is unknown is the Q that you need to Q to support, that is needed to support the voltage, and you don't know the voltage angle. Now of course there is a special case where every generator there is a Q min and a Q max. So this Q that's changing to support this voltage has to be between Q min and Q max. For example, if the generator has reached its maximum Q, then that generator bus, the voltage would be allowed to vary, and you would know the P and the Q, and it will become a PQ bus. But that's a special case. In general, a generator bus is a voltage controlled bus, so it's a PV bus. A slack bus is where the uh, delta is kept constant, or it's kept as a reference. If you see this equation up here, if you see the power flow equation, what is important is not just the voltage angle on that bus I, it is the difference in the voltage angles. So therefore you need a reference voltage angle, and this is where a slack bus comes in. And in most cases you keep delta of the slack bus as being equal to 0 degrees. Another thing to keep in mind in a slack bus, so let's just imagine you have a 4 bus system here. These 2 buses have a load. Let's say this is 100 megawatts, this is 80 megawatts, and you have a connection here, here, and here, and these 2 buses have generators connected to them. Let's say this generator is known. You have this as, let's say, 90 megawatts. Now this load is totaling up to 180 megawatts. You would think that, okay, then this generator also needs to just produce 90 megawatts. But what we don't know is there are losses in these transmission lines. If there are transformers, there'll be losses in those transformers as well. We will not know what the losses in these transmission lines are till you have all the voltages and all the power flow. So basically you have the result of your power flow solution. Once you have that solution, then you know the current through each of these transmission lines. You can find out your I square R losses. Let's say the loss in the system is let's say 20 megawatts. So then that's 180 plus 20, 200. In that case, you would need this generator to produce but this is 90, right? So this is 110 megawatts. If the loss is only 10 megawatts, then this is 190 megawatts, in which case this would have to be 100 megawatts. So in essence, this generator here is picking up the slack. Whatever quantity is unknown of the real power, that's how much this generator needs to be producing. So that is why there has to be just one generator bus in your system, that is the slack bus, which picks up the slack of the real and reactive power in the system, and it also acts as a reference for the voltage angle. So that is your slack bus. Now that you have this knowledge, let's go back and see what the options are. So once again, there are 3 buses: load buses, PQ buses, voltage control buses, PV buses, and slack buses, V delta buses. In PQ buses, P and Q is known, V and delta are not known. Here P and V is known, Q and voltage angle are not known. Here V and delta are known, and here P and Q are unknown. That's the slack bus picks up, and these are known at the end of your load flow study. So let's go back and see the options that we've been given. So we know there's only one bus that can be defined as a slack bus. So bus 2 and 4 slack buses, this is not possible. 3, 5 and 6 are slack buses, this is again not possible. Bus 1 is a slack bus, bus 1 is a slack bus. So it has to be between option C and D. Let's go see bus 1. V and delta are given. So yes, this bus 1 is indeed a slack bus. Bus 2 and 4 are generator buses. So 2, P and V are known, 4, P and V are known. So that statement is also correct. 2 and 4 are generator buses. Option D tells us bus 2 and 4 are load buses. We know that to be not true because load buses P and Q are defined. And then bus 3, 5 and 6 are load buses. 3, 5 and 6 are load buses. So this is our correct answer, where bus 1 is a slack bus, V and delta are known. Bus 2 and 4 are generator buses where P and PV are known. And bus 3, 5 and 6 where PQ are known are our load buses. So once again, I hope everything up here was a little bit clear, as well as it gave you a little bit of background as to what the load flow studies are all about, and gave you a good insight into what the equations are. But if nothing else, I want you to take away from this video that there are three types of buses: load buses, voltage control buses, slack buses. What are the known quantities in each of them, and what are the unknown quantities in each of them? So that was the focus. Once again, this was a conceptual type of video, not a numerical. I hope you've enjoyed these. I will be doing a lot more videos on power flow, so don't worry, we'll get into a little bit more of the numericals. Having said that, though, as per the guidelines for the Power PE exam, in general, each question's supposed to take somewhere close to 6 minutes. So it's unlikely you'll be tested on a numerical with reference to power flow. You might be asked something about an admittance bus or to create an admittance bus for a given system, and we'll get into that in another video. Anyways, as I mentioned, I will do more videos. And I wait for your feedback. Let me know if there was something that was not clear. If you have more questions with reference to this topic, do subscribe if you haven't already. And till next time, take care and have fun. Bye now.